In the previous lecture we have seen the definitions of attenuator and how we can express attenuation in terms of powers as well as in decibels. So now let us see what is meant by symmetrical attenuator. You all know the property of symmetry, reciprocity with respect to two-port networks, and even if you consider an attenuator, it is a two-port network because which is connected between input terminals as well as output terminals. So that forms a two-port network, and if it satisfies the properties of symmetry, that becomes symmetrical attenuator. And what else are the characteristics of symmetrical attenuator? Let us see. The attenuators which are terminated with impedance equal to the characteristic impedance are known as symmetrical attenuators. We all have discussed that there are many properties of two-port networks, parameters of two-port networks along with the Z, Y, H, G and transmission. What are they? They are image parameters, right? So out of those image parameters we have image impedances as well as characteristic impedance, and image impedances become equal to the characteristic impedance for which networks? For symmetrical network. That is what given here. So that means the attenuators for which the input impedance is equal to the characteristic impedance, otherwise the terminating impedance is equal to the characteristic impedance, are known as symmetrical attenuators. And for that kind of attenuator, if the input current is Is and output current is IL, we can have the input power output power written like this, right? Okay, so that is Is square into R naught, P2 is equal to IL square into R naught, where Is is input current, IL is output current, that is load current. And this is R naught at both places because input resistance seen from the source side as well as terminated impedance, that is output impedance, are equal here because it is a symmetrical attenuator. Okay, so we can write it like this. Then for attenuation we need the ratio of P1 by P2, right? So that ratio will be coming like this. Okay, so that ratio will be coming like this, Is square by IL square, because R naught will be cancelled. Then how to get Is by IL? It will be the under root of P1 by P2. So suppose if I have to take one single variable from these two variables, I need to define one variable like this. That is, let us consider under root of P1 by P2 is equal to capital N. It is some variable, you just consider it as some variable, like single variable for simplicity purpose. Then what happens to the N? That N becomes Is by IL because P1 by P2 is having square terms, square and under root will be cancelled out. Okay, this is about P1 by P2 ratio and capital N. Okay, and what is alpha in decibels? Alpha in decibels is equal to 10 log 10 P1 by P2, and let us substitute this P1 by P2 here in terms of currents ratios. Then it becomes alpha is equal to 20 log 10 capital N decibels. And when you write N towards left hand side, it becomes N is equal to antilog of alpha by 20. Okay, otherwise capital N will be equal to 10 to the power alpha by 20, because this alpha by 20 will be coming here and log to the base 10 N will be right side. When you take N is equal to, it becomes 10 to the power alpha by 20. So all these relations are very important. Okay, in the exams they will play with these relationships. Even in the bits you can get how capital N and alpha are related. What is capital N in the end? It is the ratio of input current to the output current. Okay, so this is about symmetrical attenuator, and of course there are several types of symmetrical attenuators based on the shape of the networks that we choose. It is just a modeling. Shape of the network means the modeling that we are going to choose. If we model the network in the shape of T for an attenuator, it becomes symmetrical T attenuator. Similarly, we can have symmetrical pi attenuator, symmetrical L attenuator, symmetrical bridge T attenuator, as well as symmetrical lattice attenuator. And we will be seeing about symmetrical T pi as well as bridge T attenuator in the coming classes, right? Thank you.